our last discussion, we talked about ethers and sulfides, how to name them, and their physical properties. Let's start now by talking about how to prepare ethers. And most of these reactions will actually be review from Organic Chemistry 1, and a couple of them will be new. So one way to prepare ethers is through the condensation of alcohols. You can see here that if I take two primary alcohols, or two molecules of a primary alcohol, and add an acid catalyst, that I get a dialkyl ether, and water as my byproduct. And the dialkyl ether, in the dialkyl ether, the two alkyl groups on each side came from the alkyl group in the alcohol. Okay, so it's a condensation reaction of two alcohol molecules. Okay, in a specific example here in the middle, we can see that if I start with two molecules of 1-butanol and use sulfuric acid as my catalyst, I get dibutyl ether as the product. The butyl groups on each side came from the butyl group in 1-butanol, and again, water as my byproduct. I can even start with a diol, where I have two alcohols in the same chain, and do an intramolecular condensation. So in 1,5-pentane diol, I have an alcohol on the left that condenses with the alcohol on the right to give me an oxane as a ring. If you think about the mechanism, you'll see that it's the oxygen atom of one alcohol forming a bond to a carbon of the other alcohol. So I form a 1, 2, 3, 4, 5, 6-membered ring. And the water molecule that I've lost comes from that OH group and that hydrogen. Okay, in the mechanism for the condensation of alcohol, you'll see that it's just a version of an SN2 substitution reaction. So if I start with ethanol, ethanol first gets protonated by sulfuric acid to give me an oxonium ion. That oxonium ion now has a good leaving group, water. A second molecule of ethanol can now add to the carbon with the leaving group. Right? We'd say that this carbon here is a very good electrophile. It has a good leaving group. Okay, so oxygen uses one of its lone pairs of electrons to add to that carbon. At the same time, I break the carbon-oxygen bond. That gives me a new oxonium ion. Now I have an oxygen with two alkyl groups attached and a hydrogen atom. Right? That oxygen is positively charged. The very last step then is deprotonation by some conjugate base. And that conjugate base could be anything. Could be another molecule of alcohol, could be water if we have that in solution, or even the conjugate base of sulfuric acid. Another method for forming ethers is by addition of alcohols to alkenes under acidic conditions. Okay, this is analogous to Markovnikov addition of hydrogen halides to alkenes. The only difference is the nucleophile that we're using. All right, to review, let's start with the addition of a hydrogen halide across an alkene. And I'm going to use a cyclohexane ring to make everything clear. Okay, so I have a disubstituted alkene. And if I react that with hydrochloric acid, actually let me make that methyl cyclohexene. If I react that with hydrochloric acid, my first step is to protonate the alkene. Right? So the electrons in the double bond are used to form a new bond to the hydrogen in hydrochloric acid, breaking the hydrogen-chlorine bond. We would say that this step is addition. Okay, so after addition, one of the carbons in the alkene is going to be protonated. Which one? The least substituted carbon gets protonated so that I generate the most substituted carbocation. Right, so this carbon now has two hydrogens. Remember that it did have one before, even though it's not drawn here. We assume that it's there. Again, Markovnikov addition. Protonate the least substituted carbon so that I get the most substituted carbocation. I always think of alkenes as doors on hinges. Right? So in this alkene, the hinge is at this carbon right here. So if the alkene swings out to form a new bond to hydrogen, at the hinge carbon, that means the other carbon in the alkene is losing a bond. Thus, it becomes positively charged. Okay, once I form the carbocation, my last step is nucleophilic addition. I have chloride in solution. After that addition step, so chloride can use one of its lone pairs to add to the carbocation to give me the final product. Now we can use the same template, only instead of using chloride as our nucleophile, now we can use an alcohol. Right? If our solvent is an alcohol, and that's the only change we would make here, we would make sure that our solvent is an alcohol. Instead of chloride adding in my final step here, we could have a molecule of alcohol added. Right? So if our solvent was methanol, the oxygen atom in methanol could use one of its lone pairs to add to the carbocation. And our final product then would be an ether. There's the original methyl group, and now here's the methoxy group that was just added. Okay, there is one final step. After that methoxy group is added, right, you'll notice that we do have to take that proton off in the end. Okay, so the final step would be deprotonation. Some conjugate base could take that hydrogen off. Could be anything. Another molecule of alcohol, could be a molecule of water in there, maybe the conjugate base of hydrochloric acid, chloride. Anything will work. That's not the important part. The important part is I deprotonate, send those electrons back to oxygen, and that gives me my final product. An ether. Okay, so again, the addition of alcohols to alkenes is just a version of Markovnikov addition. Protonate the least to get the most substituted carbocation, and then a molecule of alcohol adds to that carbocation. The question might be, why does the alcohol add and not chloride? And the answer is the concentration of the alcohol is much higher if we're using it as a solvent. Higher concentration, faster rate of reaction. Okay, so far we formed ethers by the condensation of alcohols, the addition of alcohols to alkenes through Markovnikov addition. The third method is by haloetherification. This is also a reaction that should be reviewed. Okay, so let's review quickly the addition of halogens, bromine mainly, to alkenes. Okay, remember, if we start with an alkene and we add a diatomic halogen to it, such as Br2, what happens is the double bond swings out, it acts as a nucleophile, and adds to one of the bromine atoms. That first bromine atom can be thought of as an electrophile, right? And electrophiles are either things that are positively charged, partially positively charged, or that have a good leaving group, right? Electrons that can get out of the way to make room for an incoming bond. So as the double bond swings out and adds to this bromine atom, I can break this bromine-bromine bond here. Under normal circumstances, that would give me a carbocation, right? Just saw this pattern with the addition of hydrogen chloride to an alkene. What's different about the addition of halogens to an alkene is the halogen actually uses one of its lone pairs to add back to the carbon losing a bond. And if that happens, what I get is a bromonium ion intermediate. Okay, so the alkene swung out, formed a new bond to bromine here, and then bromine used one of its lone pairs to add back to the carbon losing that bond. That gives me a 3-membered intermediate, and since bromine only has 2 lone pairs and 2 bonds now, that makes it positively charged. Right, so this was a bromonium ion. Under normal circumstances, or maybe not normal, but at least the reaction that we learned in Orgo 1, is that the last step was that bromide, let me move that out of the way a little bit, bromide adds to that bromonium ion. Right, we formed bromide after I broke that original bromine-bromine bond. It now uses one of its lone pairs to add to that carbon, breaking this bond and sending those electrons back to bromine. Okay, and again, that step is an SN2 process. So what that means is, if this bromonium ion is behind the plane of the screen, pointing backwards, the bromide ion must add from the front, inversion of configuration, so that my final product has a trans relationship between the two bromine atoms. This bromine is back, this bromine is forward, pointing towards me. Trans. Okay, to apply this to ethers, all we really have to do is start with the bromonium ion. Okay, just like Markovnikov addition. If I have an alcohol, again, instead of bromide adding, I could imagine a molecule of alcohol adding. If I use it as the solvent, the concentration is much higher, okay, and so it should add to that carbon faster. Right, so this step would be similar. Again, this would be an SN2 process. And the product that I would get is a halo ether. Again, this bromine is going to be back. And now instead of bromide forward, I'm going to have my oxygen forward attached to my carbon. I don't feel like showing that deprotonation step again, so I'm going to cheat and write minus H+. Right? You should understand by now that this oxygen atom will be protonated after the addition, and we need to deprotonate it in order to get to a neutral species. Okay, this is called a vicinal halohydrin. Alright, so haloetherification gives me vicinal halohydrins. Okay, I start with bromine or chlorine, I use an alcohol as my solvent, and then I get a trans relationship between the ether oxygen and the bromine atom. Okay, vicinal means a 1-2 relationship. Alright, our final method for the preparation of ethers is the Williamson ether synthesis. This is also reviewed. There's nothing new here. And this is just a version of SN2 substitution. Right, so in a Williamson ether synthesis, I have to start with an alkoxide, the conjugate base of an alcohol, and add to that an alkyl halide, typically an alkyl chloride, alkyl bromide, or alkyl iodide. Remember, fluorine is a very poor leaving group. Okay, and if I add those two molecules together, I should get an SN2 reaction. The oxygen is the nucleophile. It uses one of its lone pairs to add to the carbon, which has a good leaving group. Remember that to prepare alkoxides, there's a number of different methods. One of the methods that we saw in the lab in a demonstration was by adding sodium metal to alcohols directly. Right? This displaces hydrogen and gives me the alkoxide. Another method for preparing alkoxides is to treat the alcohol with a strong base. Okay? For example, sodium hydride. Hydride is the conjugate base of hydrogen gas, and it's a very strong base. Right? So if I add hydride, it'll deprotonate the alcohol to give me hydrogen gas, and then the sodium ion is the counter ion to the negatively charged oxygen. Remember that in a Williamson ether synthesis, your nucleophile, the alcohol that's going to act as a nucleophile, can be primary, secondary, or tertiary. But your electrophile, the carbon that has the leaving group must be primary, right? It must be primary. And the reason is elimination is always a possible competing reaction, right? So in this case, I have a secondary or tertiary alcohol. That's fine. But my carbon with the leaving group must be primary. Right? So if I were to make this molecule right here, right, I've got a sec-butyl group on the left, and I've got just an N-butyl group on the right. I could do a retrosynthesis two different ways. Right? I could form the bond between the oxygen and the secondary carbon, or I could imagine forming the bond between the oxygen and the primary carbon. Okay? However, the only way that will work is to form the bond between the oxygen and primary carbon. Right? So these are the two pieces that I want to use. If you tried it the other way around, elimination would be favored. We'd get an alkene. Alright, so this question wants to know which of the following ethers could not be prepared by the Williamson ether synthesis. Okay, so if I look in A, right, a logical disconnection, a retrosynthetic strategy, would be to make this bond right here. Right? I could imagine having benzyl bromide where that carbon has my leaving group, and this alcohol as my nucleophile, that alkoxide. Okay, that looks like it'll work. And the important point here is that carbon is primary. This will work. Okay, in B, okay, again, this time I could imagine having phenoxide as my nucleophile, conjugate base of phenol, and maybe using methyl iodide, right, as my electrophile. Right? That carbon is not attached to any other carbons. Right? So it will be a very good electrophile in an SN2 substitution. But when I get to C, I run into a problem. Both of these groups are the same, so it doesn't matter which bond I decide to form. Okay? So if I attempted that reaction, I would have to start with pieces that look like this. Maybe that alkyl bromide and this alkoxide. Okay? And now you'll notice that this carbon is secondary. Okay? That's not going to work. Right? Alkoxides generally give elimination reactions if the carbon with the leaving group is secondary or tertiary. So instead of SN2 substitution, what's going to happen is elimination. Right? The alkoxide is going to grab hydrogen, it's going to swing down to form a double bond, and bromide will leave. Not the product that we want if you're doing a Williamson ether synthesis. Okay, so C is not going to work here. If you look at D, that's going to work. Right? We've got a primary carbon here. So this is the bond that I should disconnect if I'm thinking backwards. And in E, I've got a primary carbon there. This is the bond I should disconnect thinking backwards. Alright, I guess the last way to prepare ethers, for now, is through the epoxidation of alkenes. Okay, this is also an old reaction, but we do want to review it quickly because the focus for our next lecture is on reactions of epoxides. Okay, so an epoxide is an ether in a three-membered ring. Right, so I've got an oxygen atom and two carbon atoms. And I can form epoxides by treating alkenes with peroxy acids. Peroxy acids look similar to carboxylic acids. The only difference is they have one additional oxygen atom. Okay, per means one additional. Alright, we won't learn the mechanism for this reaction, but the pattern is fairly straightforward. Right? It's that extra oxygen in the carboxylic acid that adds across the double bond to give me the epoxide. Right? An epoxidation reaction can be stereospecific. Stereospecific means that the stereoisomer you start with determines the stereoisomer you end with. Let's apply that to these two situations here. Okay, so is the top reaction stereospecific? Well, to answer that question, I first have to ask, what is the stereoisomer of my reactant? Is it R or S? Is it cis or trans? And if I look, there's no stereo descriptor for that molecule, right? It doesn't have any chirality centers, and the alkene cannot be cis or trans. No cis or trans possibilities means it can't influence the product of the reaction, okay? Not stereospecific. Okay, what about the bottom reaction? Does the stereoisomer I start with determine the stereoisomer I get? Well, first, are there stereoisomers of the reactant? Okay, the answer here is yes. Right? This is a cis alkene. Does that influence the stereoisomer I get in a product? The answer again is yes. This is a cis epoxide. Right? That oxygen atom in the peroxy acid has to add from the same side to both carbon atoms. Right? That means that the relationship between the two groups on the alkene won't change. If they start out cis, they end up cis. This bottom reaction then is stereospecific. Okay? One thing to note here, this reaction is not enantioselective. Right? That extra oxygen atom in the per acid can add from the front of the alkene to give me this product in the top reaction, or it can add from behind the plane of the screen to give me this product. And I would get a 50-50 mixture of both. Since these two molecules are enantiomers, I would say that I get a racemic mixture. Okay, so the top reaction is not stereospecific. It's also not enantioselective. I get both enantiomers. The bottom reaction is stereospecific, but again, it's not enantioselective. Right? These two molecules are enantiomers of one another, and I would expect there to be no preference for whether that extra oxygen in the per acid adds from the front or from the back. So I'd expect a 50-50 mixture of both. Again, a racemic mixture. Another way to prepare epoxides is an intramolecular Williamson ether synthesis. Okay, we just saw that a Williamson ether synthesis is when I add an alkoxide to an alkyl halide. Okay, well, if the alkoxide and the alkyl halide are in the same molecule, I can form a ring. Right? So I must start with a vicinal halohydrin. Again, vicinal just means adjacent, a 1-2 relationship. Remember, you can form vicinal halohydrins by adding halogens across double bonds and using water as the solvent. We just looked at a reaction similar to this for the haloetherification. The only difference is now you're using water instead of an alcohol as a solvent. First form your bromonium ion, then water attacks with inversion of configuration at one of the carbons, and you get a trans relationship between the alcohol and the bromine atom. Once you've formed that group, then you can do an intramolecular Williamson ether synthesis. If you can deprotonate the hydrogen of the alcohol, and in this example, they're using hydroxide, okay, which sometimes works. Probably a better base for deprotonating alcohols would be hydride. We've already seen that. If you can deprotonate the alcohol to give you an alkoxide, that can then act as a nucleophile and do intramolecular SN2. Right, so here's the overall process. Right, start with an alkene, form the vicinal halohydrin, add a base to get the alkoxide, which then immediately does SN2 to the alkyl halide next door to give you the epoxide. what's required for this reaction to work is that the alcohol and the halogen must be trans. They must be trans because the alkoxide that you're forming has to do SN2 to the carbon with the alkyl halide. Remember, SN2 requires inversion of configuration. That means that the alkoxide has to attack from the opposite side that the leaving group is leaving. That's only possible in a six-membered ring, at least, if the alcohol and the bromine group are trans to one another. Intramolecular cyclization of halohydrins can also be stereospecific. You can see here that if I start with a cis-2-butene, the two methyl groups on that alkene, right, start off cis, and after my two-step process, form the vicinal halohydrin, deprotonate with a base to get intramolecular SN2. After that two-step process, those two methyl groups are still cis. So if I start with a cis-alkene, I end up with a cis-alkene. Stereospecific. Another way to say it is the product that you get, or not just the product, the stereoisomer of the product that you get is specific to the stereoisomer you begin with. Okay, in the bottom example, you can see that if I start with trans, I end up with a trans relationship. The stereoisomer that I get is specific to the stereoisomer I start with. Alright, so this question wants to know which of the following transformations, when taken as a whole, is not stereospecific. Which one is not? First question to always ask, are there stereoisomers of the reactant? Right? If there are no stereoisomers possible for the reactants, you're done. Can't be stereospecific. Alright, so let's look at the top reaction. We've got methyl cyclopentene. Are there stereoisomers possible for that reactant? Well, there are no chirality centers. And the alkene has no cis or trans possibilities. Right? That alkene is in a ring. There's no way for it to be trans. Right? That's the only geometrical isomer possible. Right? So there are no other stereoisomers I can draw for A, for the reactant, and so this reaction is not stereospecific. B could be stereospecific. Right? B has a trans alkene. Right? Trans should give me a trans epoxide. Cis should give me a cis epoxide. So it looks like B could be stereospecific. What about C? Well, the alkene is not involved here, but I do have a chirality center, right there. And if I start with R, I probably get R in the product. If I start with S, I get S in the product. So it looks like C could be stereospecific. What about D? Well, I don't have cis or trans alkenes, but again, I have a chirality center here, right? And this methyl group is going to influence which direction the peroxy acid is going to approach from. Right? So remember, this is my peroxy acid. Doesn't matter what the other group, carbon group is. But this is going to add from either the top face of this alkene or from the bottom face, from behind the plane of the screen. And if the methyl group is pointing towards us, it's probably more likely to add from the back face, from behind the plane of the screen, to avoid any steric interaction with the methyl group. So since this methyl group has an influence, and since that's a chirality center, this reaction also could be stereospecific. Right? So if I start with the R methyl group, I get one isomer of my epoxide. If I start with the S methyl group, I get the opposite isomer for my epoxide. Stereospecific. What you start with determines what you get. Or more, I should say, the stereoisomer you start with determines the stereoisomer that you get. Okay, so here are my products. Okay, and only the top one is not stereospecific. Alright, your goal now is to design a synthesis of each of these epoxides. The left-hand epoxide is a trans epoxide, which means we'll probably have to get it from a trans alkene. Right? So when you're working backwards, your first step is to think, what alkene could I make that epoxide from? Okay, the epoxide on the right is a cis epoxide. The phenyl group and the ethyl group are both on the same side. So your goal is, again, what alkene can I make that cis epoxide? Probably a cis alkene.